Welcome back, cost minimization. So we're just going to continue on our journey into linear programming. Last segment we talked about profit maximization. Now we'll talk about the other major problem that we can solve using linear programming, and that's cost minimization. And as usual with linear programming questions, you sort of see a whole bunch of verbal diarrhea there, lots of relationship, lots of words. But remember, we have our three-step process. First step, find out what the decision variable is. What is it that we're deciding upon? What is that thing that we need to know that we don't already know? Then we proceed from that and we look at what's our objective. We maximizing something, minimizing something, and then we state how do we calculate that thing that we're at maximizing or minimizing. And then we'll worry about the constraints. So constraints tend to consume most of the words and most of the relationships, but the decision variable, what is the decision variable? That is actually the key component in all of this, because if we know what that is, we could figure out the rest, but if we don't know the decision variable, it's just a bunch of gobbledygook. So, with that in the back of our minds, we read, American Auto is evaluating its marketing plan for the sedans, SUVs, and trucks the company produces. A TV ad featuring its SUV has been developed. The company estimates that each showing of this commercial will cost, looks like something there important, something we might want to minimize. Cost $500,000 and increase sales of SUV by 3%, but reduce sales of trucks by 1%. That's perfectly reasonable, right? It just means we run the SUV commercial. People were motivated to buy the SUV, but some of the people would have bought our trucks anyway, so there's a little bit of a substitution effect. And they would have no effect on the sales of sedans. The company also has a print ad campaign developed that it can run in various nationally distributed magazines at a cost of $750,000 per title. It is estimated that each magazine title the ad runs in will increase the sales of sedans, SUVs, and trucks by 2% for the sedans, 1% for the SUVs, 4% for the trucks, respectively. The company desires to increase, so desires, that sounds like a requirement. Right? That's what we want. That's one of our goals. Right? One of our goals is to increase the sales of sedans, SUVs, and trucks. Kind of makes sense. By at least, right? That's setting minimum. At least means it's that amount or greater. So at least means it's going to be 3% or higher increase in sedans, 14% or higher increase in SUV sales, and a 4% increase or higher in truck sales. Right? And we want to do this in the least costly manner. So that's telling us, hey, this is a cost minimization problem. So what is it we're trying to do? Right? We're trying to increase sales. So we got our objectives. We're trying to increase sales based on these requirements. We have certain minimums, and we want to run these ads in the least costly manner possible. Well, what's driving costs? Well, the thing driving costs are the ads. So kind of looking at that and say, okay, well, that must be what we're deciding on, right? Number of ads of each respective type to run. So let's call T the number of TV ads to run, and we'll make, let's say, P for print, number of print ads to run. Okay, so there's my decision variables. Without that, it can't do any of the problem, but key, not very complicated, not very long, but so terribly important. My next step in my three-step process is, what's the objective function? Well, in this particular case, it says right there in the last or second last sentence, the least costly manner. So that means I am minimizing cost. And if I'm minimizing something, I got to have a formula or an equation or an expression that tells me how to calculate it. Otherwise, how do I know if I've made it as low as possible? So now I look at how much does it cost me to run one TV ad? Well, $500,000. If I multiply it by the number of TV ads I run, that's the total cost on my TV marketing campaign. And I add to that with the print ads. How much does it cost me to run a print ad? $750,000 for each run times by the number of times I run, times by P, and that's how much it costs. 750,000 times by P tells me how much it costs to run my print campaign. Put them together, that's my total cost for this whole marketing project, and I want to minimize that. Next step is my constraints. Now there's lots of words in there on the constraints, right? So this is the little tricky part. So I have constraints, like when we did the profit maximization, the key word there was requirements, right? Those are things that, it set limits on us. Well, desires is a limit too. It's like a requirement. And when we see that we desire to increase the sales of sedans, SUVs, and trucks by a minimum amount, those are setting some requirements for us. So we have our sedan, and I'll just call it sedan minimum, right? And we want to increase that by at least 3%. So greater than or equal to 3. You don't have to necessarily express that as a percentage, 0.03 in that case, because we're not using, percentage is the unit here. So whether you say this is 0.03 or whether you say it's 3, doesn't matter in this particular case. Now, how do I determine if I've met this requirement? Well, if I run a TV ad, what happens to sedan sales? Well, I saw at the beginning it says no effect on the sales of sedans. So 0 times by T. So it doesn't matter how many television ads I run, I'm not going to increase sedan sales. Now I kind of sift through here and when I look at the magazine, how does it affect sedan sales? Well, I see that it affects sedan sales. It increases them by 2%. So plus 2% times by P. And again, had I expressed this as proportions, 0.02, 0.03, and so on, I could have just multiplied everybody by 100 and got to the same spot. Okay? So I didn't change the essence of the equation in this particular regard because percentage is our unit of measurement for this particular constraint. If our unit of measurement were dollars, that would be a different story. Now, I get SUV minimum. Okay, and I read through the question. I say, I got to hit at least 14% on that. So minimum means that, and at least means 14% or higher. Right, so 14. Now, how did I determine that? Well, I look through the question. I say, if I run a TV ad, what happens to SUV sales? It goes up by 3%. So 3 times the number of TV ads we run, plus how much does it go up for a print ad? And I see that is 1%. 1 times P. And then I go flow down. I got a truck minimum, right? Truck requirements, truck desires. What happens with the truck campaign? Well, if I run a television ad, goes down. That's a negative number. Not good. 1T. Now, if I run a print campaign, kind of go look at the bottom, and it's goes up by 4 points for the print campaign, and my minimum there is 4%. I kind of rummage through the question a little bit, give it an extra scan to see if there's maybe another constraint there, and I don't see anything, so that's good. So now we consider our 2 implicit constraints, right? And our implicit constraints is non-integers, first of all, so I can't run a negative number of TV campaigns, and I can't run a negative number of print campaigns. I could choose not to run a television campaign. I could choose not to run a print campaign, at which those values would be 0, but I can't run a negative amount. And I'm either running a TV ad or I'm not. I'm running a print ad or I'm not. So those are restricted to be integers. Always remember those implicit constraints. And there you go. That is our mathematical formulation for this linear programming problem for cost minimization. Right? Went from decision variable to objective function to constraints. Right? Decision variable is that key component. Because if I didn't know the decision variable, none of that other stuff is going to happen. None of that other stuff is going to make sense. Right? Now I can move on to the next stage, and the next stage is graphing this thing. So just like we did with the profit maximization problem, and just like we did in Unit 6, right? I start off graphing each one of the constraints. So I have sedan, and sedan is essentially 2p equals to 3. That's the line. P equals to 1.5, and there is no t involved in this particular issue, right? It's going to be a straight line. T can go up, T can go down, isn't going to affect sedan sales at all. SUV, what do I have? I have 3T plus P equals to 14. And again, first step, always to draw the line. And so I go T is equal to 0. What must P equal to? Well, duh, P is equal to 14. And if P is equal to 0, what must T equal to? T is equal to about 4 2/3, 4.67. Okay, the rounding doesn't matter there because we're drawing it on a graph, and graphs are imprecise the best times. Truck, I have minus T plus 4P equals to 4. If T equals to 0, 4P equals to 4, so P must equal to 1. And if P equals to 0, minus T equals to 4, divide both sides by minus 1, so T must equal to minus 4. Okay. So now I have all my intercepts in order to draw my constraint line, just like we did with the profit maximization problem. Okay. A couple things to note. The largest P is 14. The largest T is 4.67, but T's got this little wrinkle here of a minus 4. So I'm just going to put the T on the y-axis, the P on the x-axis, just so that it fits the webcam nice and easily. Again, it doesn't matter. It's not like one is an independent variable and the other is a dependent variable. It doesn't matter who you put on the x and who you put on the y. It's entirely up to you. It's a personal preference. I'm just making a choice based on what's easier to draw for you. Okay, so let's draw this out. Now we want a T. Now, so we will, let's say, pick about there or so. And there's 1, 2, 3, 4, 5. And that's going to be my Y. And 1, 2, 3, 4, down on the negative axis. So there's my T, goes up to plus 5, down to minus 4, 0 somewhat in the middle. So now let's draw our P's out. And again, just making it 1 centimeter each. So 14 out there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right. And that will be my printats. Okay, so now I'm all set. So I'm going to draw out my intercepts or my lines. P is equal, sedan is P is equal to 1.5, which means it pretty much goes there. Okay. And it goes up and down, because right? It doesn't matter. The number of T, the number of television ads we run, doesn't change anything. Okay, it's just straight up and down, and I'll label that my sedan. SUV, I see if T is equal to 0, P is equal to 14, and that if P is equal to 0, T is equal to 4.67. My line between the 2 points, making sure that I label things here, and that's my SUV. And last but not least, the truck constraint. If T is equal to 0, P is equal to 1, and if T is equal to minus 4, P is equal to 0. Okay, so next step is I want to draw out my feasible region. Okay, so my feasible region will be that area that satisfies all the constraints. Okay, so if I look at sedans and it's a minimum, right? I like to use the origin sort of as a base case, and I go, okay, if P is equal to 0, is that indeed greater than or equal to 3? Well, in this case, it would be 1.5. No, right? And 2 times 0 is certainly not going to be greater than 3. So this one would be then to the right, right? Because those are the numbers that do satisfy the constraint. It's a binary world. It's a yes or no. It's either in or out. Looking at SUVs now, SUV constraint, if I plugged in 0, 0 into that equation, and I get 0 plus 0, is that greater than 14? No! Right, so it must be the other way then. So go up, so 0, 0 not in the feasible region. And then I do the same thing for truck. If I were to put 0, 0 in there, is that greater than or equal to 4? No. And so truck must also be to the right. So where is are all the constraints satisfied? Or up here, right? Up there, and up into infinity, but we're not interested in an infinite number of costs, right? So we're looking to minimize this, which means we want to bring those costs as close to 0 as we can. Of course, if we don't do any television ads or we don't do any print ads, costs are 0. Right, which in cost minimization, okay, that'd be great. But we have certain requirements, right? We want to increase sales by certain amounts, and so not running any of these ads isn't going to achieve that. But we do know we want to bring that cost function as close to 0 as we possibly can, while still meeting all our requirements. Just as we had before, we need to draw the cost function onto this particular diagram, and then pull it down towards the origin to find the minimum cost. So we make an assumption on cost. And again, the assumption is somewhat trial and error. But let's assume a cost of, let's say, $5 million. Okay. And that function is equal to 500,000 T plus 750,000 P. Tango and Papa. So if T is equal to 0, what does P equal to? Well, we would take the 5 million divided by 750,000, and we get about 6 2/3. And if the P equals to 0, T equals to 10-ish. Okay, so when we draw this out on this particular graph, we got 1, 2, 3, 4, 5, 6, and there's 1, and then it's really high. Now our goal is to pull that down. So really when we're looking at this, we really only see 2 corner point solutions here. One at 14 print ads and one where we produce a combination of print and television ads. So if we take this cost curve, and our goal now is to pull it towards the origin, kind of becomes pretty clear that there is only one good point here. Okay, this one is our optimal solution, right? Satisfies all the requirements, closest to the origin, cost minimization, pulling it down to as close to cost equal to 0 as we possibly can, while still meeting all the requirements. And now we just read this particular solution from the graph, and we see it looks like we're running about 2 print ads and approximately 4 television ads. And if we plug that into our cost equation, That's 500,000 times by 4 plus 750,000 times by 2. And we are looking at about $3.5 million. Now, if we wanted an exact number, we know that the constraint for truck is binding, right? Because it's part of the optimal solution, the corner point's optimal solution, and the constraint for SUV is also binding. So we could just find an intersection of those two constraints of SUV and truck and solve for that just like we did in unit number 2, and that would get us an exact amount. Graphs give us an approximate, that would give us an exact amount. But I'd be very surprised if it deviated much from the 4 and the 2. And that wraps it up, and there is our whole formulation from stating it mathematically, the problem, to solving it graphically.